Lesson: Hyperparameter tuning concepts. Hyperparameter tuning is a critical aspect of machine learning model optimization that significantly influences the predictive performance of AI systems. In the realm of AI performance optimization, particularly within the scope of the Certified AI Implementation Professional course, a profound understanding of hyperparameter tuning is essential for professionals striving to implement AI models that are not only accurate, but also efficient and reliable. Hyperparameters are the parameters set before the learning process begins, and their configuration can drastically alter the outcome of a machine learning model. Unlike model parameters that are learned from the data, hyperparameters are specified by the practitioner and must be meticulously adjusted to balance bias and variance, ultimately enhancing the model's generalization capabilities. The process of hyperparameter tuning involves selecting the optimal set of hyperparameters that minimizes a predefined loss function on the validation dataset. A well-tuned model is one that not only performs well on training data, but also generalizes to unseen data, thereby reducing the risk of overfitting or underfitting. This tuning process is often iterative and requires a systematic approach to evaluate the impact of hyperparameter combinations on model performance. One of the most fundamental methods for hyperparameter tuning is grid search, which systematically explores all possible combinations of a predefined hyperparameter grid. Although this exhaustive search guarantees finding the optimal solution within the grid, it is computationally expensive, especially for large datasets and complex models. In contrast, random search, another popular technique, randomly samples hyperparameter combinations. While it may seem less thorough, random search has been shown to be more efficient than grid search in high-dimensional spaces because it can explore more diverse configurations with fewer iterations. However, both of these traditional methods can be enhanced with modern optimization strategies such as Bayesian optimization. This probabilistic model-based approach iteratively updates beliefs about the optimal hyperparameters by evaluating the performance of sampled configurations. Bayesian optimization intelligently balances exploration and exploitation, making it a powerful tool for hyperparameter tuning in complex models. Practical tools that facilitate hyperparameter tuning are crucial for professionals aiming to implement these concepts effectively. Scikit-learn, a widely used machine learning library in Python, offers built-in support for both grid search and random search via its grid search CV and randomized search CV classes. These tools allow for cross-validation, a technique that further aids in assessing the model's ability to generalize by splitting the dataset into multiple subsets and training and validating the model on each. Additionally, for more advanced hyperparameter tuning, libraries such as Optuna and HyperOpt provide frameworks for implementing Bayesian optimization, enabling more efficient exploration of the hyperparameter space. A practical application of hyperparameter tuning is evident in the tuning of deep learning models, where the number of layers, learning rate, batch size, and optimizer type are critical hyperparameters. For instance, in a case study involving the tuning of a convolutional neural network for image classification, researchers utilized Bayesian optimization to identify an optimal configuration that outperformed traditional tuning methods in both accuracy and computational efficiency. By systematically adjusting these hyperparameters, the researchers were able to significantly enhance the model's performance, illustrating the practical impact of effective hyperparameter tuning. Moreover, hyperparameter tuning is not limited to improving model performance. It also plays a crucial role in resource management and operational efficiency. An example of this is evident in the use of hyperparameter tuning to optimize the performance of AI models deployed in cloud environments. Given the cost implications of computational resources, finding an efficient hyperparameter configuration can lead to substantial cost savings while maintaining or even improving model accuracy. This is particularly relevant in industries where AI models are part of large-scale production systems, such as finance or healthcare, where operational efficiency is paramount. To address real-world challenges, professionals must also consider the trade-offs between model complexity and interpretability, especially in sectors where transparency is crucial. Hyperparameter tuning can aid in finding a balance by optimizing simpler models that provide sufficient accuracy while remaining interpretable. For example, in a healthcare application involving risk prediction, a decision tree model may be preferred for its interpretability. Hyperparameter tuning can be used to adjust the tree's depth and the minimum number of samples required at a leaf node to ensure the model is not only accurate, but also transparent enough for stakeholders to understand and trust its predictions. In conclusion, hyperparameter tuning is an indispensable component of AI performance optimization. By leveraging practical tools such as scikit-learn, Optuna, and HyperOpt, and employing strategies like Bayesian optimization, professionals can effectively enhance the performance of their AI models. The integration of these techniques not only leads to better accuracy and efficiency, but also addresses broader challenges such as resource management and model interpretability. As AI continues to permeate various industries, the ability to optimize hyperparameters proficiently will remain a valuable skill for AI implementation professionals, enabling them to deliver high-performing and reliable models that meet the demands of real-world applications.